Ever get this feeling like you think you're starting to understand something, like how the universe works?
Yeah.
You think you've got the basics, then bam, something comes along and just totally changes the game.
Yeah, definitely. Like when you find that missing puzzle piece, but it turns out to be from a totally different puzzle.
Exactly. And that's what today's deep dive is all about. This really mind-blowing moment in physics, this discovery that really shook things up. Parity non-conservation.
And the cool thing is, we're going straight to the source for this. Tsung Dao Lee's Nobel lecture, from 1957, he won the Nobel Prize for this very discovery.
It's like getting a backstage pass to a scientific revolution. But don't worry, we're your guides, here to break it all down. No PhD required.
Yeah, we'll be your physics translators for the day.
So to really get into it, we need to start with the fundamental building blocks of, well, everything, right?
Yeah.
And those are elementary particles.
But think of them like the universe's tiniest Lego bricks. Some are heavier, like protons and neutrons, the guys hanging out in the nucleus of an atom.
Right, the heavyweights.
And then there are the lighter ones, like photons, the particles that make up light, or electrons, those little guys zipping around the nucleus.
And there's this rule in physics, a really important one, called the law of conservation of heavy particles. Catchy name, right?
Definitely rolls right off the tongue.
Basically, it means that those heavy particles can't just disappear, vanish into thin air. Imagine if they could, what a mess that would be.
Right. Talk about chaos. Your coffee cup suddenly morphing into a beam of light.
Thankfully, this law prevents our universe, including us, from just dissolving into a soup of lighter particles.
Keeps things interesting, for sure. But here's the thing. If these particles are the building blocks, what's holding them together? What's dictating how they interact?
I'm sensing a but coming.
But of course there is. That's where the fundamental forces step in. They're calling the shots, governing all those interactions happening in the universe. And there are a few different flavors of these forces.
Okay, let's talk forces. I'm ready. All right, forces. Lay it on me. What kind of forces are we talking?
So we've got the strong force, the electromagnetic force, and bringing up the rear, the weak force. And they each have their own, shall we say, personality.
Okay, this is already sounding more interesting than my high school physics class. So what makes each of these forces so special?
Well, the strong force, like the name suggests, is the strongest of the bunch. It's the one responsible for holding those atomic nuclei together, like superglue for protons and neutrons. Without it, atoms would just spontaneously fall apart.
So it's like the bedrock of matter, keeping everything from flying apart. Got it. What about the electromagnetic source?
That one's responsible for all things electric, magnetic, light itself. Pretty important for our everyday lives, wouldn't you say?
Can't argue with that. Okay, that brings us to the weak force. What's its deal? It sounds kind of, well, weak.
Deceptively weak, my friend. It governs things like radioactive decay, kind of like the ticking clock inside unstable atoms.
Right, radioactive decay.
Mhm.
So not exactly something we encounter every day, at least I hope not. But these forces, they weren't just acting randomly, right? There were rules, symmetries, that physicists thought were fundamental to, like the very fabric of the universe.
You're exactly right. And one of those big ones was the concept of parity.
Symmetry in physics. That sounds kind of abstract.
It is a bit abstract, yeah. It's not like, atoms lining up to admire themselves in a mirror or anything.
Okay, good. Glad I'm not the only one who pictured that.
Parity symmetry is more like saying the laws of physics shouldn't care if you're looking at the universe directly or through a mirror. It should all work the same way.
So you're saying if we could flip the entire universe, like a pancake, everything should, theoretically, keep on ticking like nothing happened.
Precisely. And for a long time, every experiment, every observation seemed to back that up. The strong force, the electromagnetic force, they were playing by the parity rules.
But then, the weak force.
Yeah.
That's where things get really interesting.
You could say that again. This is where our story takes a turn.
Give me the details. What was this experiment that changed everything?
Picture this. A brilliant physicist, Chan Shengwu, designs this incredibly elegant experiment using cobalt-60, which, as we know, is radioactive.
Okay, setting the scene. Cobalt-60, radioactive, what else?
Well, they had to get these cobalt-60 atoms really, really cold.
How cold are we talking? Colder than my wife's feet in winter.
Way colder. Think a fraction of a degree above absolute zero, which, by the way, is really, really cold. They needed those atoms practically frozen in place. Then they apply a magnetic field to line up the spins of all those cobalt-60 atoms. Imagine, like, tiny little compass needles all pointing in the same direction.
Okay, I'm visualizing these perfectly aligned, super chilled atoms.
Yeah.
What happens next? This is where the universe throws us a curveball, right?
You bet. So those cobalt-60 atoms, they start to decay, right? And when they do, they emit electrons.
Okay, makes sense. Radioactive decay emitting electrons.
But here's the thing. If parity symmetry held true, those electrons should have flown off randomly in all directions. The direction of those electrons, it shouldn't have cared one bit about how those cobalt-60 atoms were spinning. But that's not what they found.
Don't keep me in suspense. What happened?
Those electrons, they had a preference. They weren't flying off randomly at all. They preferred to shoot off in one specific direction. And get this, it was directly related to the spin of those decaying cobalt-60 atoms.
Whoa, are you serious? So the direction of those electrons actually depended on which way those cobalt-60 atoms were spinning. That's crazy.
Crazy but true. That, my friend, was the first undeniable evidence that this weak force, unlike the strong and electromagnetic forces, it does not obey parity symmetry.
Talk about a plot twist. It's like the universe suddenly revealed it has a mischievous side, like it's playing by its own set of rules. This wasn't just some fluke, right? Did they see this parity violation happening everywhere?
You're right on the money. It wasn't a one-time thing. It wasn't just limited to cobalt-60. Remember those other particles we were talking about earlier? Pions, muons, lambda particles. They all have a little dance with the weak force at some point.
Right.
And guess what? They all showed the same parity violation. It was a pattern deeply embedded in the weak force itself. It was basically saying, hey, those parity rules, they don't apply to me.
This is blowing my mind. So how did physicists wrap their heads around this? What could possibly explain this blatant disregard for the established laws of the universe?
Well, leave it to those tricky little neutrinos to shake things up. They had an answer, or at least a pretty elegant theory. It's called the two-component neutrino theory.
Okay, neutrinos to the rescue. I'm intrigued. Tell me more. What's this theory all about?
So imagine neutrino, like a tiny little spinning screw, right? It can spin in one direction relative to how it's moving, we call that right-handed, or it can spin the opposite way, which we call left-handed. Now, here's the wild part. This theory says that in our universe, we only really have right-handed neutrinos and left-handed antineutrinos. They're mirror images, so to speak.
Hold on. So it's like the universe has a preference for right-handed screws. Lefties need not apply.
You got it. It's like somewhere along the way, the universe decided to go all in on one type of spin for neutrinos. And this inherent asymmetry baked right into the neutrino's existence, it explained the whole parity violation thing with the weak force. See, the weak force, it only interacts with these specific types of neutrinos, and that's what creates that bias in the direction of those emitted electrons we were talking about earlier. It's like the universe was winking at us, saying, look closer, there's more to this than meets the eye.
Wow. I'm starting to see how this tiny, almost invisible particle plays such a huge role in our understanding of the universe. It's like those neutrinos were holding the missing piece of the puzzle all along. But this wasn't just about neutrinos, right? This discovery had bigger implications, didn't it?
Absolutely. It all ties into another fundamental concept, the conservation of leptons. Remember that rule about heavy particles, how they can't just disappear? Well, there's a similar principle for a group of particles called leptons, which includes our friend the electron, and, you guessed it, neutrinos.
So no disappearing leptons either. That's reassuring, at least.
Exactly. The total number of leptons in a closed system always stays the same. This law, when you combine it with that quirky two-component neutrino theory, it starts to paint a pretty amazing picture, even if it is a bit mind-boggling, of how these particles behave at the most fundamental level.
It's like a cosmic dance, with all these particles and forces following their own choreography. So after diving deep into the quantum world, it's clear this discovery was monumental. But what's the takeaway message? Why should we care about a bunch of rule-breaking particles?
This wasn't just about tweaking a few equations in a textbook. Parity violation, it totally changed how we understand the universe. It showed us that the universe isn't as simple or as symmetrical as we once thought. It was a reality check, you know? It forced physicists to re-examine their assumptions, to dig deeper and explore new possibilities in particle physics. And who knows what other surprises are still out there, just waiting to be discovered.
It's both humbling and exhilarating, realizing how much we still don't know about the universe. There's so much more to explore.
Exactly. It's like that feeling when you stand at the edge of the ocean, looking out at the vastness, a sense of awe and wonder. That's what physics does. It reminds us that we're part of something much bigger than ourselves.
Beautifully said. And on that note, we'll leave you, our listeners, to ponder the mysteries of the universe. Until next time, keep those brains buzzing, and thanks for joining us on The Deep Dive.